Yes? Okay, yeah, I wanted to tell you about a recent project I've been working on in Stefano Fusi's lab at Columbia with Daniel Bendai and Rubin, and more recently with Serjan Ostojic. And the whole project has been carried out in collaboration and strict interaction with Daniel Salzman lab, so a monkey electrophysiology lab, and in particular with Sarah Morrison and Alex Saez, who are recording in the amygdala and the orbitofrontal cortex of behaving monkeys. So, yeah, let's jump right in. Say you're walking down the streets of Jerusalem, you're in Ben Yehuda, and you come across this stimulus, right? It's a falafel sandwich. I don't know, you decide to buy it, eat it, and it turns out that it was a good decision. It's a very good falafel. And I don't need to tell you after Peter Dayan's presentation, but now what people usually posit is that this positive influence the falafel had on you is going to generate some reward prediction error, which in turn associates a positive value to this falafel. So let's say now that you take a plane, fly to New York because you're attending next year's Gatsby meeting, and you're walking around the Columbia Medical Campus and come across a food cart which displays the same kind of stimulus. Now the falafel though is associated with a very positive reward because of your previous Israeli experience, and so you decide to buy it and eat it, but turns out it was not a good idea in this context. Yeah. I don't know why, they use this white yogurt sauce instead of the trina, and they stuff them with the colorless salad, and they never change the oil in the fryer. So it's what the TD error, that the TD learning algorithm does is devaluating, in this case, the falafel. So, well, this raises a problem, right? The fact that you override the previously acquired positive value associated to the falafel basically makes so that you won't be able to distinguish between good and bad falafels. Basically, you see a falafel, it's going to recall a negative value. And the way this problem has been solved in the literature is just to basically assume that you instantiate two versions of the falafel, one which is which will correspond to an hidden context, a hidden state corresponding to the context in which you are in Israel, so positive falafel. And accordingly, we'll have a negative falafel which is associated to the Columbia University context. So why is this important? The idea is that, well, this will allow you to basically change the value of the falafel when you're in the United States independently for the value of the falafel when you're here. It's also important because some people propose that this kind of mechanism, this creation of hidden contextual states, is a possible way to explain phenomena like renewal after extinction. So the idea would be that you acquire, well, in this falafel metaphor, you acquire a positive value for the falafel, you extinguish it, but then what happens in a renewal framework is that you can reacquire a positive value much faster than you did during the first try. So the way we want to, well, the questions we want to address then in this kind of framework is, number one, where are and how are these values created in the brain? Number two, how do we create this contextual, this hidden state, this internal representation of the context? And number three, how do these factors interact? So, fortunately, we have, again, I told you we are collaborating on this thing with Professor Daniel Salzman at Columbia. They work on monkey electrophysiology, and it turns out that they have a very controlled laboratory setting to study this kind of task and behavior. So the task they're working with is very similar to the one which was presented by Hagai Berman a few hours ago. It's actually even simpler. It's a trace conditioning task. So the monkey is presented with two possible stimuli, let's say stimulus A, and after a small delay, which they call a trace period because they're psychiatrists, the A stimulus is followed by a reward, which consists of a few drops of juice delivered in proximity of the mouth of the monkey. Another stimulus, say B, will instead be followed by an air puff. Yeah, I also didn't write aversive, but I thought it was clear that it's pretty aversive to the monkey. These animals start to scream and kick whenever they get this air puff on the face. It's pretty annoying to them. So yeah, a difference between this and Bergman's task is that this is a one-to-one mapping. So this A stimulus is always paired with a reward. This B stimulus is always paired with an air puff. And an important similarity is that, well, the fact that a guy pointed out, that is that there is, even if it's a classical conditioning task, there is a very important instrumental component. And that is the fact that when monkeys see A, they actually have to start leaking in order to drink the reward which is delivered, otherwise the drops will get lost. Similarly, when they presume they're going to receive an air puff, what they can do is start blinking so as to basically try to screen their eyes. This also, moreover, allows the experimenters to assess whether the monkey has learned the association. So if during the trace period the monkey starts blinking, it means that the monkey learned that A is going to be associated with a reward. But if it starts blinking in this trace period, then, well, it clearly means that the monkey has learned that B is carrying a negative value. And once the monkey have learned this association, what they do is very vicious. The experimenter reversed the associations, and the monkey has to relearn them. So, actually, a way to formulate this task is the following. We can say that basically there are two contexts, right? Two temporal contexts. One in which A is positive and B is a punishment. And the second context in which A is negative and B is positive. So notice that both contexts are defined solely by the temporal relationship between the elements. So in particular, there is no cue which explicitly tells the monkey that the context has changed. The only thing things which define the context is the fact that A is reliably followed by a reward, B is reliably followed by the air puff in context 1, and vice versa for context 2. So actually what we assume now is that if the monkey is presented with several blocks which alternate context 1 and context 2, so at first the monkey will learn context 1, forget it in favor of context 2, but as this alternation goes on, the monkey has the interest of learning that there are two different contexts, and this will allow it to switch its behavior in a much faster way once it realizes that the context 2 has been activated. So actually what we can ask is this really what happens? Does the monkey learn the representation of these two contexts? And so to check this, what we can do is basically look at the behavior, right? What we can predict if we assume that the monkey has learned. Yeah?
The two contexts are on the same amount of time each time, or could they switch random?
The switch happens when the monkey has reached some performance, so 90% performance, and then they switch. Yeah, let's look at the behavior and see whether in fact the monkey has learned these two context representations. So what we can predict if we assume that the monkey in fact possesses these representations is that, well, when we are in context 1, the monkey is presented with A, licks, gets a reward. It's presented with B, blinks, get an air puff. Presented with A, licks, get a reward. And then let's assume that now the experimenters they decide, well, I'm going to introduce a reversal here. So the monkey is presented with A, And what does it do?
Leak.
Exactly, yeah, it will leak because that's what it learned it had to do in proximity of A. But well, it turns out that it gets an epoch, but because they decided to reverse. And it's going to be a very silent reversal. And if the monkey now, in fact, has this representation, it will realize, oh, well, the context has changed. That means that now if I'm presented with B, it means that I have to leak as well, right? Because now in the second context, B has become positive. So basically, the idea is that here, seeing that A has changed allows me to generalize and basically infer that also B has changed. So, okay, this is the behavioral evidence. In fact, what happens is exactly what I showed you in the previous slide. So this is the percentage of leaking at the presentation of the condition stimulus X, when X was unrewarded and the monkey didn't leak. And after the switch, after the first presentation of the other stimulus, CSY, the monkey already starts leaking, even though it never seen context X in this condition stimulus X in this context.
It's never seen a context switch, no? This is the first context.
No. The monkey has already. Sorry. The monkey has already seen a lot of blocks.
Context.
Yeah, exactly.
This is
This is after
after
like a few weeks of training. Analogously, what happens if the monkey, it reverses the behavior for the opposite stimulus. Yeah.
There was a paper a few years ago, I think, coming from the lab of Miller, sure, where they showed that monkeys don't, in similar conditions, there was no voluntary word learning association. Monkeys were unable to learn the context.
Yeah, it's true.
Once they made a mistake, they started from scratch.
Yeah, so there are a few things. That task was slightly more difficult. It was an operant task, so the monkey had to do something.
But here the monkey also had to do something. Leak.
Yeah, it's true. But you may argue that it's more natural to the monkey to leak. It's something which is basically involuntary, right? But actually, wait. Let's see.
I'm not familiar with the other paper, but monkey learning.
in that paper they had a lot of distractors.
Yeah, exactly. Another thing which was different, it was not blocks of, there were several stimuli and only a few reverse, something like that, if I'm not wrong. So it was considerably more difficult. So some reversed, some didn't. But actually what's similar is in fact that after the first error, the monkey at the very, well, we will see it later. Okay, so this is the network model we want to propose. First of all, let's see what kind of neurons we see, if you recall, in the amygdala and the OFC. This is published data. It's what Sussman's report is. The report is that the amygdala, in fact, contains some neurons which are selective for the positive and negative values. So this is a trace of two neurons. This neuron here has a higher activity when a negative stimulus is presented, so either A or B, while this one is in the OFC has a higher activity when positive stimulus. So okay, this is a very easy element to implement in a network. It's basically we assume that there are two populations, a positive value coding population, a negative value coding one, and you just implement some sort of reinforcement learning to learn these these two populations have to compete, and that, for instance, A has to activate plus, B has to activate minus. But what this network would do is actually resetting at every switch. It will never get the context, obviously, because it doesn't have it built in. So there's something missing, right? And what could it be? So we are pretty agnostic how we should model that part. So what we do is starting just by introducing some random neurons, which is a leitmotif of several talks in this workshop. So the idea here is that I have a population which is randomly connected to these other neurons, and they will display some sort of mixed selectivity to combinations of stimuli and values. For instance, this neuron here, B minus, will be activated when I present B and B has a negative value. So it will look like this. It only responds when B is negative, otherwise it's always silent. For instance, this neuron here, A plus, will look pretty much like this, so it has a preference for A when A is positive. And well, you have all sorts of other combinations, like this neuron here, 0A, which responds when A is presented and nothing is active here, or this R0, which is active when the reward is presented, and so on. So do we have these kind of neurons in the biological system we're observing? Turns out, yeah, we do. These are actually recordings, because once we realized that these neurons could be of interest, we went back to Salzman's data and tried to look for them. It turns out that these kind of neurons are useful because, as you can imagine, as you can see, this neuron here, which one is it? Yeah, this neuron here basically codes for this contingency, which is basically half of the context one, while this neuron here codes for the other half of context one. So if there was a way to link the activity of these two neurons so that whenever I activate this neuron, its activity drags the activation of this other neuron along, then that would allow me to create some sort of representation of the context, right? This kind of selectivity, this mixed selectivity, is an extensive variable in the observed data. So this is an analysis of variance of the selectivity of the neurons in amygdala and OFC. Turns out that 30%, between 30 and 40% of the neurons have this mixed selectivity. So they display an interaction factor which is significant if you do a two-way ANOVA.
So the A and B stimuli are the same throughout training, or
yeah,
you tried it also with?
They are the same in every session. So you change them when you change day, every day.
Every day you change.
Yeah.
So do you see the same behavior even if you use completely new stimuli? Well, but at some time it should realize that there's the context switch regardless of what the stimulus is.
We actually didn't try that. It's certainly going to be more difficult, right? So I don't know. We didn't try it, but it's true. You may think that. Well, what you would see. Our hypothesis is that. So the representation of the stimuli somehow matters in this experiment, but you may think that. I don't know. The monkey may infer some meta rule which allows it to generalize to this more complicated case, but I don't know, we didn't consider that case. So again, once you have a way to link the activity of this neuron with the activity of this neuron, then what you have to do is, well, introduce some sort of feedback so that the activity of this CN network, which I call CN because it's been denominated a context network. So the activity is fed back to this associative network and allows to modulate the response so that basically encapsulate the essence of this context. Okay, so what does our model assumes? It's basically the idea I just told you, but what I want now is to connect the activity of this neuron with the activity of this other neuron. And a way to do it is based on the fact that context one is defined by the statistical regularity given by the fact that A is reliably positive in this context and B is always negative. So basically what happens in this context is that the activation of A plus tend to be followed by the activation of B minus. So if I introduce some synaptic learning rule, which basically potentiate synapses between neurons which are activated in sequence in this way, so that this will allow me to basically link the activity of these two neurons together. So at this point, I mean, the assumption is that because of this sequential activation, the synapses will become so much potentiated that this small population will start to become self-sustained. Yeah?
Sorry, so that alternating activation pattern happens at the time scale of trials, or?
It's it's immediate. The idea is that I don't know. It's the UDT in your simulation, whatever. No, I will show you a simulation run. It's yeah, but
what's the time?
But my I don't know, my I can have that potentiation be within. Actually, we will assume that it's within a microscopic time scale. So yeah. So we don't have any eligibility trace or anything. We will see. So at this point, the idea is that I have this attract of the neural dynamics, and I can use it to feed back the information to the associative network, and make it basically encode the context. Okay, we need another element though. So the fact that you don't want this attractor to be sustained throughout the block alternation, right? When a reversal comes along, this attractor has to be deactivated. So the additional element we have is the assumption that whenever you activate a neuron which is not in this recurrent population, this will somehow start a competition with this other population and deactivate it. So everything will shut down. So in this specific case, say, okay, this population is active. I have a reversal, so the monkey was expecting a positive value, but it gets a punishment instead. So these neurons here, which code for this combination of events, will activate, and deactivate all the network. And okay, this will allow me, because I deactivate this will allow me to activate the opposite context representation and bias the activity of the A network in the other direction. So okay, this is pretty much the model. It's as simple as you can get. It's a binary neural model. It's super simple because we were interested in the interaction of the activity and the learning role. So we try to keep it as straightforward as possible. So every neuron is represented by a binary variable. So this is a heaviside of basically the recurrent activity. This I is the activity of the rest of the population, which is fed back to this neuron. And this H denotes the external stimulus. So these J's are the synapses. They can be between 0s and 1. This is actually it's basically the feedback of an inhibitory population, and this is just a threshold. The learning dynamics is pretty much what I told you. So actually, there are two components. One is an Hebbian plasticity component, so this is just an Hebbian term. This is a corresponding LTD term. And we have additionally this term here, which basically corresponds to a learning margin, which is pretty much what Omri told you about the other time. So it's something which basically stops learning when the direction of the current into the neuron agrees enough with the activity of the neuron. So apart from this Hebbian term, we have a temporally asymmetric term, this delta JA term, which is basically the same thing, but instead of the presynaptic activity, I have the activity of the network at a previous time step, and instead of the postsynaptic activity, I have the external stimulation of the following time step. So it's essentially okay. There's another term. This delta T gates the learning whenever the pattern of the recurrent activity corresponds to the external stimulation.
S and A.
So S is, this means symmetric, that is symmetric in time, and this means asymmetric.
And you do both?
Yeah, we do both simultaneously. Let me maybe show you what happens in the simulation, just to give you an idea. So, okay, this is a depiction of a simulation. This is the onset of A, onset of reward, B, and punishment. This is the activity of the association network. So A is presented. The network knows that A is positive, so it activates the positive population. And then when reward is delivered, it deactivates it. And the same thing for the B punishment. So this is what happens in the CN network, which runs with the dynamic mix I just showed you. So these are all these neurons which mix selectivity to the value and the external stimulus. For instance, when A comes along, the neuron with mixed selectivity 0A will be activated. And it will correspondingly inhibit all the other neurons in the network, which I denote with this darker blue line. Then when A and plus overlap, this will activate A plus, and so on. When reward and plus overlap, this will activate plus and reward. So the first thing which kicks in.
What's time step in network in terms of this time step? Many time steps per small red
Yeah. So yeah, this is one time step. Every square is one time step. So we set the learning ratio, the learning rates in such a way that the first thing that kicks in is this JS term. So what happens is that because A plus, well, because all these populations are activated very frequently, they start to be reverberating activity. So they start being attractors of the neural dynamics. So when A plus is activated, the activity will continue throughout the trial until plus R is activated, which will inhibit all the rest, and correspondingly shut this attractor off, and so on for the rest of the trial. So the second, the second thing which kicks in is a fusion, is this JA term, which basically links the activity of this plus R neuron with the activity of this R0 attractor. So what happens here is, as you can see, is that this asymmetric synaptic term has become so strong after a few blocks that when I activate plus R, this will in turn activate R0 as well, because it's the population which is most reliably activated after plus R. Okay, I continue iterating in this way. So I have A plus, which is reliably followed by the activation of this compound here, and this will now generate this kind of dynamics. So as soon as I present A plus, this will activate all these neurons, and so on. Now, if I zoom out, what I will see is that, so this is, every one of these colored marks represent a block of 120 trial or something. And after I don't know, say 20 block alternation, what you can see is that you get these tribes, right? Which basically tell you that here, during context 1, this blue stripe, I have the activation of this pattern of activity, which corresponds to actually the representation of context 1, because A plus is active, and so is B minus. So yeah, I have to tell you actually that I set the parameters in such a way that this fusion stops at this point. So basically, the idea is that this Hebbian synaptic term starts to compete with the JA, so that the fusion stops at this point, and otherwise everything would be activated. Okay, so let's go to the prediction of the model. The first one is what we started out trying to model, that is that we have some sort of generalization. So as soon as I activate this A+ neuron or population, its activation drags along the activation of this compound. And so I can use this to bias the activity of the DAN and represent the context, so that basically I have this switch. So this generalization which is represented here, actually what I want to depict here is the fact that as soon as the network learns that A is positive, it activates the whole compound, so it automatically knows that B is negative. So this is the percentage of time that the network gets the second stimulus correctly after the first one is correct. This is in the case in which I don't have the context network, and this is the case in which I have the context network. Well, this agrees with what is observed behaviorally, right? So the fact that the monkeys start leaking the presentation of CSX, even though it never saw it before. So the second prediction is something which is related to the question you asked me. So I think I have to think more about that. The fact that so context 1 is active, so it biases the activity to represent this context. And now I have a reversal. The reversal will activate this one of the neurons which is not in this population here, and so that will deactivate everything. So what happens is that since nothing is activated on the network will respond stochastically.
But this is not what is in experiment. In these experiments that you're trying to explain. And you started by saying that you learned.
Yeah. It's
The one after the first.
this is exactly. This is after the first error,
Correct is not.
and before it was after the first correct response. So here I respond according to context 1, then I get it wrong, I deactivate everything, and the result is that I respond 50-50. On the other hand, if I respond...
So every time you make a mistake, you go back to chance level.
Basically, yeah.
And this is what you see in these experiments?
We didn't think of analyzing the data in this direction, but you see this behavior in other experiments. Like this is a paper by Keiji Tanaka's group, in which they also have two rules. The rules are more complicated, and what happens, in fact, I did this slide yesterday. I didn't think of analyzing the data, our data, in this direction, but I remembered about this paper. What they see there is that, again, they have two rules, and once the monkey makes a mistake, somehow it resets everything. It goes to 50-50. So I think either one of the rules at random.
But weren't you unhappy with the initial Edmond model because it would reset rather than switch?
Yeah, actually, oops, sorry. No, I wasn't unhappy because it could not reinstate context 1 after a switch, or context 2 after the switch right away.
But that's a matter of learning rate, right?
Yeah, but this goes beyond learning rate, right? Because you never, like, for instance, here, the monkey has never seen condition stimulus X, but still it responds correctly because of seeing the other stimulus.
You made a mistake in the other one.
I don't understand.
No, okay.
Extra consistent.
I didn't. Yeah, maybe the next. So this is after the monkey got at this in this plot. This is where the system gets the first association, and so also the second one is realized, as opposed to making a mistake and resetting everything.
said that you started to say that the behavior is that after the first error, it immediately switches.
No. It's after the first correct response on one stimulus, it correctly predicts the second stimulus. But after one mistake, it deactivates it.
What is a mistake?
So for instance, I think that A is positive, but instead it's negative.
So that's...
So what happened?
But that's what you said.
No, it's different.
Leak and you get a tail path. This is a mistake, no?
It's a mistake.
Then you see B and you leak. So this is...
No, but at the no. What happens is that, okay, I leak.
Because the first cartoon was
okay, so...
Yeah, it's true.
It just happened to
Yeah.
50-50, right?
Yeah, once as soon as you get it right for one stimulus, then you get it right for the second one, which is what we wanted to model when I said that we wanted to be able to generalize across the stimuli. But once I get one wrong, then I go to the stochastic behavior. So, okay. So this is electrophysiological data. So another prediction of the model is that you will have neurons which are selective for the context, right? And so this is basically, these black lines denote the selective okay, let me go back. So every line is a cell, and for every cell I draw a thick mark whenever the cell is selective for the context. So for instance, this cell here, which has two thick marks in the intertrial interval, will look like that. It will look like something in which the activity during context 1 and context 2 is distinguishable. And I don't know, for instance, this cell here, let's say, will look pretty much like this. That is, it has a differential activity during context 1 and context 2 during the trace interval. Actually, these are data, so this is what you observe. When the monkey displays the behavior which indicates that it learns the context, then you can also observe it at the level of the neural activity. Another prediction we were unable to check actually is the simplest one, right? So that the idea is that as soon as the monkey learns the representation of the context, then what happens is a neuron which used to be selective for A+, or a neuron which used to be selective for B- rather, will start being selective also for A+, because when I present A+, this neuron will be activated, and it will automatically activate this other neuron. So yeah, this is work in progress. We could never see these things happening because just because you have to be able to learn to record throughout a session in which the monkey basically learned the context. But it's something we're trying to work on. Okay, conclusion. We exploited mixed selectivity in order to represent and create in an unsupervised way a representation of the context. In order to do that, we use a temporal plasticity rule, which relies on the activation of temporal contiguous activity patterns in a network of attractor with attractor dynamics. And here, the resulting attractors can be used as neural representation of temporal context. These are the people I work with. Stefano Fusis. In Stefano Fusis' group, David Ben-Dayan, Rubin, Serge Nostich, Omri. And in Daniel Satzman group, Sarah Morrison and Alex Seitz. Thank you.